All right, today we're diving into a document that's literally the foundation for some of the most critical software on the entire planet, the Mil-Std 498 Software Requirements Specification. You can think of it as the blueprint for code that absolutely positively cannot be allowed to fail. And we're about to find out exactly why it's so important.
I mean, just imagine you've got that job. The stakes? They couldn't be any higher. A single bug, one tiny little misunderstanding in the code, could lead to absolute catastrophe. The sheer complexity is just overwhelming. So how in the world do you get a team of hundreds, maybe even thousands of brilliant engineers to build the exact same thing, down to the last detail, perfectly?
Well, that's the core of the problem, isn't it? If one engineer thinks fast means it has to happen in under a second, but another engineer thinks it means under 50 milliseconds, you've got a disaster just waiting to happen. In these mission-critical systems, ambiguity isn't just a minor issue, it is the enemy.
And this right here, this is our weapon against that enemy, the Software Requirements Specification, or SRS. Now, it defines all the requirements for any given piece of software, what the document calls a CSCI. But here's the really crucial part, the thing that sets it apart. It doesn't just list what the software must do. It also specifies exactly how you will prove that it has been done.
This is probably the best way to wrap your head around it. You know, before a single brick is laid for a massive skyscraper, there's a ridiculously detailed blueprint that everyone, the architect, the engineer, the construction crew, they all agree on it. The SRS is that blueprint, but for code. It becomes the one document that the customer, the project manager, and the developer all look to. It is the single source of truth.
So, here's our game plan for breaking this blueprint down. First, we're going to see how it brings order to what could be total chaos. Then, we'll dive into the software's core mission and see how it connects to other systems. After that, we'll get into the really strict rules for quality and safety. And finally, maybe the most important part, how you prove that the whole thing actually works.
All right, first up, let's take a look at how this document itself is structured. To turn the potential chaos of a massive software project into a calm, orderly, and manageable process.
Yeah, this isn't just a suggestion or some good idea someone cooked up. It's a formal government standard. This title page here signifies that the entire process is built on a foundation that has been battle-tested and refined over decades in some of the most demanding environments you can possibly imagine. This document means business.
Now, let's get to the real heart of the document. This is where we stop talking about the process and start defining, with almost painful precision, what the software's actual job is.
And this right here points us to the absolute core of the SRS, Section 3.2, Capability Requirements. You can think of this as the contract. It's where you state every single function the software has to perform. Notice, it's not how it will be built, but precisely what it will do when it's all finished.
And look, a capability isn't some vague description of a feature. The standard forces you to get specific. What are the response times? And they better be measured in milliseconds. What's the throughput? How many targets can it track at once? And this is so crucial. What should it do when things go wrong? Every single possibility has to be considered and written down.
So, knowing what the software has to do, that's really only half the battle. Software almost never works alone. So the next critical step is defining exactly how it's supposed to communicate with the rest of the world. I mean, think about the flight control software on an airplane. It has to get data from hundreds of sensors, send commands to the engines and all the control surfaces, and display critical information to the pilot, all at the same time. If those communication links aren't perfectly and unambiguously defined, nothing works. And this is where your mind might just get a little blown by the level of detail we're talking about. This table shows just some of the attributes you have to define for every single piece of data that crosses an interface. Is the altitude measured in feet or meters? To how many decimal places of precision? Who is even allowed to see this data? This is exactly how you prevent disasters like the Mars Climate Orbiter, which was tragically lost because one engineering team used metric units and the other used imperial. It all comes down to this level of detail.
Okay, so the software might function correctly, it might communicate perfectly, but is it actually good? Is it reliable? Is it safe? This next section defines those all-important rules of engagement. Section 3.11 forces developers to think way beyond just pure functionality. See, it's not enough for the code to work on day one. It has to be reliable, easy to fix, and simple to use for years to come. These quality factors are really what separate professional-grade mission-critical software from just a hobbyist project.
So you have to define these things right up front. Reliability, how often is it allowed to fail? Maybe once every million hours of operation. You write that down. Maintainability, how long should it take a brand new developer to find and fix a bug? Portability, can this code be moved from one type of computer to another without a complete rewrite? These factors are every bit as important as the features themselves.
And when we start talking about safety, well, the stakes become crystal clear really fast. This is a direct quote from the standard section on safety requirements. The document literally forces you to think about the worst things that could go wrong and then explicitly write requirements to prevent them. This isn't abstract stuff. This is about preventing a pilot from accidentally turning off the autopilot at the worst possible moment.
And that brings us to the final and, perhaps the most critical piece of this whole puzzle. After you've created this incredible, detailed blueprint, how do you actually prove that the final product matches it perfectly? For every single requirement in this massive document, you have to specify how it will be verified using one of these 5 methods. For a requirement like the indicator light must turn green, you can use demonstration. You just look at it. But for something like the response time must be under 50 milliseconds, you're going to need a test with special equipment. Nothing, and I mean nothing, is left to chance. Every single claim is proven.
And finally, there's this idea of traceability. This rule is so simple, but it is incredibly powerful. It ensures that there are no rogue requirements. Every single function the software performs has to trace all the way back to a specific, documented need from the customer. This is the ultimate weapon against scope creep. It prevents engineers from adding unnecessary features, it reduces complexity, and it makes sure you only build what is absolutely essential.
So that brings us to the big question, right? In a world that prizes moving fast and breaking things, a document like this can feel like, well, a relic. It can seem like a lot of bureaucracy. But when the software you're building simply cannot break, is this level of meticulous, painstaking detail the only way to guarantee you succeed? It's something to think about. Thanks for tuning in.